Okay, welcome to your AP problem walkthrough video. I'm going to do a few conceptual questions just to help you a little bit with the tricky naming patterns between ionic and covalent. Metallic is really easy. I'm actually not even sure if I mentioned it in the pre-lecture video, but the metallic name is just the metal itself or some other name that we gave it that's very conventional. I'm going to really just focus on ionic and covalent naming rules and parsing out the structure because that's really what the AP focuses on. And I'll walk you through a really short molecular polarity question, and then we'll do one short FRQ mainly. It won't be complete because you haven't learned the rest of it, but you'll get through one. I'll put the timestamp in for the AP question. However, if you are struggling a little bit with the concepts of naming, or the rules behind naming, as well as a little bit of polarity, I highly recommend that you watch this first conceptual part. So starting on page 1, we just have a series of naming requests for you. So remember with molecular that we can't figure out through math how many atoms are in the compound. We can't figure out the constant composition, the law of constant composition. We can't figure out the molar ratio between the atoms. We can't figure out the ratio of the atoms, the subscripts in that molecule because it is sharing, right? If it is covalent, it is sharing electrons, which means we really have to be told, okay, how many atoms are involved for each element, for each composition, okay, compositional element. Otherwise, we wouldn't know because we don't have true charges. We don't have true math that we can rely on. So what we would do is we use Greek prefixes, all right, to just straight up tell the audience member what our compound structure is for a molecular compound or a covalent based molecule. And we say disilicon is Si2. And remember, we're dealing with subscripts here because we're talking about the ratio of atoms bonded together, right? Trioxide, oxygen in a bond and 3 of them, okay? How about for ionic compounds? Now that's different. Ionic, right, has a full transfer. So that means we can use the charge values, okay, to predict the subscripts or the law of constant composition or the proportions or the ratio between the atoms bonded. So what we have here is potassium carbonate. Now, potassium is an alkali metal that always carries on a 1+ charge. Carbonate is a polyatomic, a group of covalently bonded atoms that together act like one giant ion. And here it's acting as one giant anion. And it is CO3. Okay, you should be memorizing these, by the way, 2-. So it carries a 2- charge. So what we have then is, in order for our cation and our respective anion, which again is a group of atoms that acts as one anion, okay, to have them cancel out to build a stable ionic compound, we say that, okay, the name is, or sorry, the chemical formula is K2, because I'm going to need 2 potassiums to cancel out the 2- charge, carbonate. Okay, one of those. And since there's only one of them, I don't need to put a parentheses around it because we assume that you're acquainted well enough with chemistry that you can spot a polyatomic if I don't put a parentheses around it if there's only one of them. Okay. And then of course you're asked to think backwards. Okay. So here we have selenium. That's our first element, our more positive element usually. And by the way, it will become usually our more centered element, the element that's in the middle and everything else is coming off of it. Selenium. Okay. Chloride. Okay. Selenium dichloride. Selenium dichloride. Because these are 2 nonmetals. So I just made a great example of a mistake that you can make is look at the types of atoms bonded, and that can give you a really good idea of what type of molecule you have. So here I have 2 nonmetals, and 2 nonmetals bonded usually means that you are doing a covalent molecule, right? You're doing a covalent bond. Now, there was that exception with hydrogen and fluorine and a couple of those like extreme hydrogens and any halogen, just because of how great the electronegativity difference is. We categorize it as ionic despite it being two nonmetals. But generally speaking, selenium, nonmetal, chlorine, nonmetal. So they're going to form a covalent bond. They're going to share. They don't have that much electronegativity difference. And so therefore we need to use Greek prefixes. Okay. And then for the last one, L, this is an example of a hydrate, okay, an ionic compound lattice structure with little water molecules kind of trapped in there. So what we have is we have sodium, okay, monohydrogen phosphate, or there's a couple names for it. There's sodium, monohydrogen, one hydrogen, phosphate, okay, heptahydrate, a 7 heptahydrate, a 7 water molecule with a 7 water molecule ratio, or this could also be called sodium biphosphate, okay, heptahydrate. Both are valid, okay? Notice you have the ionic compound portion right here. This is the ionic compound, and it's named according to our ionic compound rules, right? And then you have this molecular portion of it, or covalent portion of it, and it's named using covalent rules, heptahydrate, Greek prefix, okay? So that's just kind of a little review. Naming is really just being familiar, right? Like if the real reason for all of this is that when the AP or any type of examinative exam gives you a prompt and they give you a molecule, you really need to know how to say it, how to call it, and how to read the formula or write the formula from the name. So let's just look at question 2. I'm just going to go through one of them. How do we identify, how might we write a preliminary chemical equation for how an ionic compound is formed from their respective ions? Well, here we have chromium, and chromium is a transition metal, so it's multivalent, so we need to tell you the charge. So we say chromium 3 plus based off of that Roman numeral 3, and oxalate. Okay, oxalate is a unique polyatomic. You don't necessarily have to memorize it, but it might be one of those things that having it in the back of your head memorized might help you. Okay, C2O4 is the oxalate structure, and it's a 2 minus ion. And so what is the structure that would be, what is the ionic compound that would be created? Well, in order to cancel out charges, I'm going to need to have 2 chromines, okay, 2 chromine ions come together with 3 oxalate ions, because 2 times 3, right? And 2 times -3, right? Gives me 6 minus, okay? Or actually, sorry, I realized I miswrote that. 3 times 2 minus, or 2 negative gives me 6 minus charge. This gives me a 6 plus charge, so I know they're going to cancel. And that will give me the overall compound of Cr little 2, because now they're in a bond, okay? C2O4, and 3 of those polyatomics, okay? C2O4, 3 of them. Now, I want you to notice something. How when I initially wrote the initial ions required, I put the 2 and the 3 out front, because what I'm saying is that I need of each of these ions. They're not bonded yet. So I'm going to just write overall, I need 2 of these ions and 3 of these ions to come together. But once they're in a bond, I turn those larger numbers, we call them coefficients, into the small subscripts to represent these are now the ratio for this compound. This is now indicating to me the law of constant proportion, the ratio of atoms bonded together. And notice I did write parentheses here because it's not C2O43, right? I need 3 groups of C2O4. All right. So let's go ahead and move on to a little bit of polarity. Here we have Pauling scale provided to you, and I say complete the following table by writing out the formula. and determine the electronegativity value, and then classify the individual bond as nonpolar, polar, or ionic. So for this, here we have, okay, the compound formula. We have rubidium and oxygen. Notice it is a metal plus a non-metal, which is usually characteristic, right, of an ionic compound, a metal plus a non-metal. So I'm going to be metal. Oops. Just immediately notices it's a metal plus a non-metal. So most likely we're going to get an ionic compound. And what we see then is we have rubidium. Okay, let's highlight this. Let me do rubidium oxide. Oh yeah, those are huge electronegativity difference. You have a formula between rubidium and oxide. We know that rubidium is in the alkali column, which means it's going to take on a +1 or a 1+ charge. Oxygen is going to take on a 2-. So we know that immediately, just from the names of the elements and where they fall in the periodic table, this is going to be ionic. Okay, and it's going to have to charge cancel. It's going to engage in that type of bonding. So we're going to look at our charges, and we're going to say rubidium has to have 2 of them, okay, bonded to 1 oxygen to create a stable ionic bond or compound in general. And how do we confirm this? Conceptually, through the concept of electronegativity values, right? Well, we have rubidium, the absolute value difference between rubidium, which is 0.8 electronegativity, and oxygen is 3.5, gives us an electronegativity value that is very large, which is 2.7. And so that is how you can kind of look at one. You can look at just the elements involved and usually know what type of general bond you're going to get. But then 2, you can always use electronegativity differences to confirm, all right, and to support. So you can fill out the rest of the table. I just wanted to go through one of them. And along with that, here is just one more quick walkthrough of how to do question now 13. Consider the electronegativity values and use the following elements: Al, aluminum, chlorine, Cl, nitrogen, and sodium to form an example of each type of compound. And then write the chemical formula. So for one of them, I say form a compound with an ionic bond, which means I am going to choose out of these 4 combos. I need to choose, right, 2 atoms, one of which who is mostly a metal and a non-metal, because I don't see any polyatomics as my options, one of which is a metal and a non-metal to form a bond with an electronegativity difference, okay, greater than 0.4, ideally, okay, and not greater than 1.7. So what I'm going to do is I'm going to look at aluminum, and right now I only have 2 non-metals. So I have 2 non-metals and I have 2 metals. So it's going to be a combo of 1 metal with a non-metal. So when I look at aluminum and chlorine, okay, aluminum has a 1.5 and chlorine has a 3. Oh, well, that's a 1.5 difference. So right there, I just kind of figured out an ionic bond combo. So let's do aluminum and chlorine would have an electronegativity. Ooh, you know what? Aluminum chlorine only has an electronegativity difference of 3 minus 1.5, which is 1. Oh, I see. I made a mistake. I want ionic. Oops, sorry guys. So I want my electronegativity difference to be greater than 1.7. I apologize. My bad. I want my electronegativity difference to be greater than 1.7 to be considered ionic. So when I look at aluminum chlorine, that won't work because it's only a 1.5 difference. So what about aluminum and nitrogen? Also a 1.5 difference. So that won't work. Okay. How about sodium and chlorine? Let's do sodium and chlorine. I'm doing green. Sodium, and I'm going to kind of erase that, and chlorine. Okay, that's a difference of, all right, that's a difference of 0.9 and 3.0. Okay, 0.9 and 3.0. That gives me an absolute value difference of 2.1. That is definitely ionic, right? That's definitely ionic. So then we could say, now that we've identified a bond, okay, that is supported through electronegativity calculations to be ionic, all right, Now I need to create the correct formula using my rules of ionic that for the charges must cancel. So when I look at sodium, it's also in the 1 plus, and chlorine is going to be in the 1 minus column for ionic charge take on. And so what I say is that my bond, my chemical formula is NaCl. Okay, awesome. So let's quickly do AP question now. Short FRQ. Oh, actually, this is a long FRQ. I apologize. This is a long FRQ, which would be allotted 23 minutes, 10 points on the AP exam. We're only going to do parts A, B, and C. So for the first part, you are given a giant prompt. Okay, actually, no, you're just given the instructions. Not a giant prompt at all. That's very nice. And you're asked to tell me what type of chemical bond is present in the Cl2 molecule. So immediately, okay, your brain should notice that this is a diatomic molecule. This is a diatomic molecule. And diatomic molecules, okay, always engage in molecular, right? And you would know this partly because the electronegativity difference or covalent, molecular covalent are pretty interchangeable. The electronegativity difference would be 0 because it's the same atom bonded to itself. So automatically, you know this is going to be a non-polar, okay, covalent bond. So what type of chemical bond is present in this Cl2 molecule? Well, the diatomic molecule would engage / form a non-polar covalent bond. Okay, non-polar covalent bond. So Cl2 reacts with the element strontium to form an ionic compound. Okay, so now I'm saying Cl2 is going to react with strontium in some fashion to create some strontium chloride combo. Okay, and so however that looks like, right? We don't quite know what these are, but we know it's going to be bonded and it has to be ionic. Based on the periodic properties, identify a molecule, X2, let's give it that is likely to react with strontium in a way similar to how chlorine reacts with strontium. So here's what you need to think of immediately. Periodic properties immediately is an indicator right there for periodic table trends. You should immediately be thinking of, oh, periodic table trends and similar, okay, properties down a column, right? Similar properties for elements down a column, right? So what is another diatomic molecule that would behave in a way similar to chlorine when it reacts with strontium? Well, another diatomic molecule, okay, would be any halogen diatomic, such as, you could list any, such as fluorine, right? Or bromine, okay, would behave similarly, or I think it says would react, would react in a similar way as chlorine, okay, diatomic chlorine, because it is part of the same family or group, or however you want to say it, right? So what you're going to start noticing is as we progress in our units in AP chemistry, your AP questions are going to become far more comprehensive and include a lot of unit knowledge that isn't just about that one unit. Okay, finally, C, a graph of potential energy versus internuclear distance, or the distance between the nuclei of two atoms for two chlorine atoms. Okay, so we're looking at chlorine 2, right? Same and same. Okay, is given to the right. On the same graph, carefully sketch a curve that corresponds to the potential energy versus internuclear distance for two bromine atoms. So here's the thing that you're going to be asked to do is they're asking you to consider, okay, well, what's the one difference, all right, between bromine and chlorine? Okay, well, bromine, first of all, is larger. It's in an energy level. Bromine is larger. So that means that the distance between the two, all right, nuclei is going to be greater internuclear distance. All right, greater internuclear distance. So that means that your overall shape of your potential energy bonding curve, which looks similar, right? There's going to be an ideal bond length between them that has the lowest potential energy, signaling high bond energy, signaling stabilization, right? But what's going to happen is that your internuclear distance is greater. It's the only difference really between these two. So it's going to shift over more to the right so that you see the curve is the curve or the points of potential energy being achieved are occurring at a slightly greater distance between them. So what you'll probably get is something like this, and you'll see that, okay, curve. And what you'll also see is that the curve itself might be a little, okay, might be in addition a little higher. Oops, I think I just have to redraw it, delete. Might be the dipping point might be a little bit higher than chlorine because when you have greater distance between them, you have also less nuclei attraction occurring just because they're slightly farther apart. So you have a slightly weaker, okay, Coulombic attraction occurring between the atoms, nuclei, because of the distance. So bond energy is a little lower. Or another way of putting it is the potential energy is a little higher. So potential energy, okay, the lowest point of the potential energy is a bit higher. All right. Okay. So that's how you would draw this potential energy curve. And that's also great practice of how to read them and interpret them, and then of course apply them. So really good job, you guys. Congratulations. We're kicking through the units.